There is a maximum rate at which the voltage at the output of any op-amp can change. This is called the slew rate of an op-amp. It is a time domain parameter, and it is usually measured in volt per microsecond. This is the technical data sheet of a Texas Instruments op-amp. This data sheet is for the LMV116 and the LMV118 op-amps from Texas Instruments. For these op-amps, the output voltage slew rate is 40 volts per microsecond. What determines the slew rate of an op-amp? An op-amp has an internal capacitor, which forms part of the dominant pole or low-pass filter. The charge current supplying this capacitor is limited. So, it takes time to charge this capacitor. The time it takes to charge the capacitor determines the slew rate. This is what the model for the slew rate looks like. It is a pulse current source, charging a capacitor. In this slide, we shall analyze the operation of this circuit, before we introduce it into our op-amp model. This is the equation that describes the relationship between the capacitor charge current and voltage. This equation can be manipulated to show that the rate of change of the capacitor voltage is equal to the charge current divided by the capacitor value. This means the larger the capacitor, the slower the rate of rise in the capacitor voltage. Or, the higher the current, the faster the capacitor charges. Let's use a numerical example. The current is 1 milliamp, and the capacitor is 1 nanofarad. The example reduces to a slew rate of 1 volt per microsecond. This graph shows the 1 milliamp pulse current in green, and the linear rise in the capacitor voltage in red. The gradient of the red curve is 500 millivolts per half a microsecond. When simplified, this reduces to 1 volt per 1 microsecond. In this slide, we are adding the slew rate circuit to our op-amp model. We are already familiar with the non-inverting amplifier model that we used so far. This is the schematic for the ideal op-amp, with the output clamp circuit, introduced in the previous section. And this is what the circuit looks like when we add the slew rate circuit. The slew rate circuit is circled in red. Note that the input to the slew rate circuit is a voltage-controlled current source, G1. The gain of this voltage-controlled current source is 1 milliamp per volt. In this slide, we are exploring the effect of the slew rate circuit on the op-amp performance. This is done using a square wave, because a square wave shows the effect of the slew rate clearly. This is the LT Spice schematic we are using. The input signal is a square wave, with an amplitude of 1 volt, and a frequency of 1 kHz, or a period of 1000 microseconds, as indicated in the schematic. The rise and fall times of the square wave are both 1 nanosecond, which is quite fast. These values have deliberately been specified to be fast, so that the effect of the slew rate can be illustrated more clearly. The duty cycle is 50%. This is what the input signal, shown as the red curve, looks like. The output signal is shown as the green curve. Note the increased rise and fall time of the green output curve, relative to the red input curve. In this slide, we continue to explore the effect of slew rate on a square wave. This is the LT Spice schematic from the previous slide. It shows the signals at various points within the op-amp model. First, is the input signal in red, still with an amplitude of 1 volt, duty cycle of 50%, and frequency of 1 kHz. Second, is the signal in green, at the output of the slew rate circuit. Third, is the signal at the output of the op-amp, which includes the clamp circuit. The effect of the slew rate is clearly visible in the output signal, when seen relative to the input signal. Note that there is a slight phase shift between the red input signal and the purple output signal. More about this later. Here, we explore what the effect of changing the slew rate is on the output signal of the op-amp. We change the slew rate by varying the value of the capacitor in the slew rate circuit. This is the result of the LT SPICE simulation for 4 different capacitor values. The dot step command was used to vary the capacitor value. The capacitor values used are 10 nanofarad, 50 nanofarad, 100 nanofarad and 150 nanofarad. Note that there is an increasing delay in the output signal as the capacitor value increases. We need to investigate what causes this, which we shall do next. This is the LT SPICE schematic file that is provided. It contains the schematic for the ideal op-amp, the schematic for the ideal op-amp with the clamp circuit added, and the schematic for the ideal op-amp circuit with the clamp and slew rate circuits added. Use this LT SPICE file, with the title shown in the slide, to run the LT SPICE simulation. Vary the values for R1 and C1, the slew rate circuit components, and observe the effect on the output signal. Compare the input and output signals by plotting them on the same graph. This is the best way to analyze the effect of the slew rate circuit. Also vary the input waveform parameters and wave shape. For example, change the wave shape to a sine wave, and vary the frequency. Observe the effect of the slew rate circuit on the sine wave. Note that this is a time domain simulation. This is the LT SPICE schematic to simulate an aspect that was pointed out earlier, which is the increasing delay in the output signal, caused by increasing the value of C1. The delay is caused by the clamp circuit at the output. The delay happens when the output signal is clamped. Use this LT SPICE file, with the file name as shown in the slide, and simulate the slew rate circuit for various conditions. Observe the effect of these variations in the time response of the output signal. Note that the dot step command is used again. This command can be used to vary any of the circuit component values, or parameters, over a range of values. This is the end of the slew rate section. In the next section, we introduce the concept of input offset and add it to our LT SPICE model. So far, the model includes the ideal op-amp with the output clamp circuit and a slew rate circuit.